Hello and welcome back to Calculus 1. This is the part 2 on graphing functions. Last time we talked about the list of things you would need and then did 2 examples. Today we're going to take a look at a little bit spicier cases. So let's start with graph f of x is equal to ln of x squared plus 1. So graphing this by hand. And the way you do it is you run through those calculations from the list and you will get points and asymptotes and all of the things that will guide your graph to be graphed. So we start by from number 1, domain. So we know that for the domain of ln function, we can only use positive numbers. 0 and negative numbers are not the part of the domain because they make the ln give either infinity, negative infinity, or complex numbers. But now we have x squared plus 1. And if you think a little bit about it, x squared will always give you a positive number, no matter what x you plug in. And plus 1 will make sure that it's never 0, which is why we have negative infinity to positive infinity on domain, all real numbers, because there is no way to make the argument of ln, right, the stuff in parentheses, there's no way to make it negative or 0. And that gives us the domain. Now we go into the x and the y intercept. So for x-intercept, we set ln of x squared plus 1 equal to 0. We e both sides to solve for x. We get x squared plus 1 equals to 1, from where we get x squared equals to 0, and we get x equals 0. When you plug in x equals 0 for y value, well, no, actually, you set y to 0, so you know y is 0. So you get 0, 0, and that is your x and y intercept at the same time because it's in the intersection of the graph, right, at the origin. 3. Vertical asymptote, none, because there are no interruptions in the domain. That's one of the prerequisites. Horizontal asymptote. Well, we are supposed to run the limit of x goes to infinity of ln of x squared plus 1. Now to solve this, we will interchange limit and ln. So you'll take limit of x squared plus 1 and that goes to infinity. Therefore ln of infinity is infinity. So no horizontal asymptote, and clearly none for the slant asymptote because slant asymptote only happens when you divide polynomials. So no asymptotes of any kind. All right, that was quick. Now we need the first derivative. Well, the first derivative is going to be x squared plus 1 and then 2x on top. That's the derivative of ln. You always copy the argument in the denominator, right? This is something that is going to be on your exam in 2 days. So derivative of basic ln functions. You know that you are supposed to copy the denominator as is, right? Copy the function in the denominator as is and then just take its derivative in the numerator. All right, so now we need the second derivative. For that we can use quotient rule. X squared plus 1 squared, x squared plus 1 times 2 minus 2x times 2x. This is going to be 2x squared plus 2 minus 4x squared divided by x squared plus 1 squared for a total of 2 minus 2x squared divided by x squared plus 1 squared. So now I have the first and the second derivative, so I can go and get my first derivative test and then later second derivative test. So for the first derivative test we need critical points. So 2x over x squared plus 1 equal to 0. When you cross multiply you get 2x equal to 0, x equals 0. So we know that there is a critical point at 0, 0. We already had point 0, 0 before, so now we need to figure out whether this point is a min or a max. And we do that through increase, decrease, partitions, and all of that good stuff. So we have a 0, negative infinity to positive infinity for our domain, and we choose any test points we want inside the interval. So now we have f prime of negative 1. That's going to be 2 times negative 1 divided by negative 1 squared plus 1. This is negative 2 over 2, which is negative 1 less than 0. We have a decrease on the left, and then we do the same thing for positive 1. We'll get 2 divided by 2 this time, which is 1. It's larger than 0. We have increase. So what we get from this is we get that this point is a minimum. We get that free of charge, right? Because we figured out that the function is decreasing up to 1 and then increasing after. Number 6 is the second derivative test, which will give us concavity. And we take second derivative set equal to 0, so that's 2 minus 2x squared divided by x squared plus 1, everything squared. And when I set this equal to 0, we get 2 minus 2x squared equal to 0. You can move 2 to the other side. You get x squared equals to 1, x equals to plus minus 1.
You just skip like what, factoring that out, or?
You can do the factoring if you want to, but you can also move the term and then divide by 2 both sides. Right? And we need the y values. So y is f of negative 1, which is ln of negative 1 squared plus 1, which is ln 2. And then another one, which is now ln of 1 squared plus 1, which is also ln 2. Oops. So I have 2 inflection points, positive 1 and ln 2, and negative 1 and ln 2. Now we partition using those inflection points. I have 2 of them, one at negative 1, one at positive 1. And we can pick negative 2, 0, and 2 as our test points on the interval. So yes, you can remember, right, the procedure for first and second derivative test is identical, except the second derivative test uses second derivative. And the points are inflection points rather than critical points. But the procedure is always the same. You just compute everything. I have my second derivative here, so it's going to be 2 minus 2 times negative 2 squared divided by, I'll just put something positive because we really don't have to compute these things. We just need the sign. So this is going to be 2 minus 4. 2 minus 8. So that's a negative divided by the positive. That's going to be less than 0. So we have a concave down on the first one. You can compute, if you don't want to do the analysis with signs, you can just compute the entire, like I computed here. right? I computed everything instead of analyzing the signs. All we care about is whether the answer is smaller or bigger than 0, which is why playing the game of positive and negative is sufficient. But if you are not comfortable with that, then just, compute everything to the end and you're done. 2 minus 2 times 0 squared divided by something positive, because denominator will always be positive because the whole denominator is squared. That always produces positive numbers. So I have now positive divided by a positive that's larger than 0, so I have a concave up in the middle. And then f double prime at 2 is going to be 2 minus 2 times 2 squared divided by something positive. It's going to be negative divided by positive, again less than 0. And we have a concave down. That's it. We can graph. So we know that there is nothing less than y equals 0, because the minimum point for the problem was at 0, 0. And when you have a minimum point, you put a little smiley through it, so you know it's a minimum point. Then you go out -1 and +1, and use your calculator to calculate ln of 2, so you can have these points. So this point over here is 1 ln 2, and this point here is -1 ln 2.
If you don't have a scientific calculator, it does ln.
Mm-hmm.
So if you don't have a scientific calculator, it does ln on a test.
Yeah.
Could you just put 1 comma ln 2, or?
1 ln 2 is perfect. I mean, that's great. But it's just, you don't know where to, if you don't know the values, or you don't know at least approximately what the values are, and you don't have the scientific calculator, then you don't know where to put this point in terms of the y value, right? That's the issue. All right, so what do I have? Well, it says that up to 0, x equals 0, you have a decreasing function. And you have to connect these 2 points. And so to have a decreasing function, it's going to come in like this, go through this point, and then into the minimum. It's going to emerge on the other side, because now on the other side it's supposed to be increasing function, and go through. So it's important to see that the wings, right, on the sides are both concave down, and the middle is concave up. So the middle over here is like x squared, concave up, and all of these sides on the other side are concave down. So you can see that the first derivative test said this is going to be decreasing, and it's decreasing. The first derivative test also told you that this is going to be increasing, and it is increasing. As you're walking on it towards the right, you're always going up. And then the first derivative also, the second derivative test said that you are going to have concave down on the edges. We can actually bring that, see, concave down on before -1 and after +1, we have concave down. And this is concave down. And you have concave up, right, like this in the middle. So it's concave up in the middle. So the whole thing falls into place. We had no asymptotes to graph and worry about. And you were able to graph ln of x squared plus 1 without use of calculator. It's how you honor your ancestors, right, who had to do these things without the calculator. Now that you have access to your graphing utility. Let's do one more problem and then be done. With this, we'll switch to review. Now I'm going to give you some time to enjoy this. So let's say that f of x is equal to x squared ln x. X squared ln x. So you know the list of all the things that you guys should calculate. We go one by one. Okay, let's take a look. Domain. We start at the domain because we don't want to deal with values that are not in the domain. It's a waste of time, right? Now, domain is always restricted by the most restrictive function present. X squared has all real numbers. ln x has only positive values. So 0, yes. No 0. To infinity is our domain. Number 2, we set this equal to 0. It's not in the domain. Not in the domain. And then we also have ln x equal to 0, from where x is equal to 1. Now that one we get to keep, x equals 1, so we have 1, 0 as our x-intercept. Now for the y-intercept, we set x equal to 0, but then you have 0 times ln 0, no solution. So we have no y-intercept. 3, vertical asymptote. Well, ln has vertical asymptote at 0, so there is an asymptote x equals 0 because of ln x. If you place 0 bit of x squared ln x as x goes to infinity, and we get infinity, so none, and slant asymptote also none, because it's not polynomials dividing, right? Good. So that's that. We have x squared times ln x, so it's a product rule. Copy the first times derivative of the second, which is 1 over x, plus ln x times derivative of the first is 2x. When you simplify this, you get x plus 2x ln x. So this is our first derivative, and we need second derivative as well. So I'm going to circle the first derivative in blue, and now, oh, I forgot to circle the asymptotes. There we go. So now the first derivative here would be, the second derivative here would be 1 plus, and now we have another product rule. So copy the first times derivative of the second plus copy the second times derivative of the first. And when we cancel these x's, we get 3 plus 2 ln x. And that's our second derivative. And now we can do first derivative test. And for the first derivative test, we have x plus 2x ln x equal to 0. Now, the way to solve these problems is to factor x, 1 plus 2 ln x equal to 0, and then set each one of these equal to 0. Now, first one has no solution, right? X equals 0. We have to throw that away, not in the domain. And we attempt to solve the second one. The second one, we have 2 ln x equals negative 1. ln x equals negative 1/2. And when you e both sides to kill off the ln, you actually get that x is equal to 1 over square root of e, because you have a half is the root, and negative sense in the denominator. So we have that x is equal to 1 over e. So now we can calculate the y value for this, because this is going to be either a minimum or a maximum. It's going to be something, right? So y is equal to function computed at 1 over square root of e, and that's going to be 1 over square root of e squared times ln of 1 over square root of e. And as you are computing this, you get 1 over e times ln of this would be, this was e to the negative 1/2. So it's just going to be negative 1/2. So the whole thing is negative 1 over 2e. So we have a critical point at 1 over root e, comma, negative 1 over 2e. And we have to see what that thing is. So to do the first derivative test, we know there is a vertical asymptote at 0. And we are going to positive infinity. There is another partition at 1 over root e. So these are, the first one is the vertical asymptote, and this one is the critical point. Now we pick two values in between. The easy value obviously here is 1, because you have a fraction that is smaller than 1. And now the trick to pick value in here is to pick a positive number, because it has to be bigger than 0, that has a denominator bigger than 1 over root e. And now we run first derivative test at 1 over e, and our first derivative is x plus 2x ln x. So x plus 2x ln x. There we go. And all of these values are positive because, oh, lies. ln of 1 over e is negative 1. Lies. Hold on. We have to compute this. We have 1 over e plus 2 over e times negative 1. Because ln of e to the minus 1 would be ln and e cancel, and then so this is 1 over e minus 2 over e, which is negative 1 over e, less than 0, so we have a decrease over here. And f prime at 1 is 1 plus 2 ln of 1, which is ln of 1 is 0, so 1 plus 0, which is 1, which is bigger than 0. So we have an increase. And what we get for free is that this point is a minimum, because the function goes down, hits this point, and then bounces up. And that's how the minimum is made. Now we're going to go and do the same thing for the second derivative. So second derivative test. We are going to take our second derivative, 3 plus 2 ln x, and set it equal to 0. So when you move the 3 to the other side, divide by 2, we get ln x is equal to negative 3/2. We e both sides to get x out of ln. X is equal to e to the negative 3/2. So this is where inflection point is. We can find its y value by plugging this e to the negative 3/2 into original problem, which is x squared times ln x. So e to the negative 3/2 squared times ln e to the negative 3/2. The squaring will kill the half, so we have e to the negative 3 times ln will kill e. You just have negative 3/2. So this is going to be negative 3 over 2e cubed. And that's our inflection point. E to the negative 3/2, comma, negative 3 over 2e cubed. That's a point to graph. Again, you'll get the decimals using the calculator. And we do our partition now. We have two partitions again. Starting at 0, there is no domain like before 0. There's nothing there. So function starts after 0. And we have e to the negative, well, let me put it this way. 1 over e to the 3/2. We know that we just need to make denominator larger, and then we'll have smaller number. So we are picking again the point at 1, and then we have in here we can use 1 over e squared, because 3/2 is 1.5. 1.5 is smaller than 2. The larger the denominator, the smaller the overall number, because it's 1 over, right? So 1 over e squared would be the smaller value. And now we just run the second derivative here at e to the negative 2. Second derivative was 3 plus 2 ln of e to the negative 2. This will be 3 minus 4, which is negative 1 less than 0, concave down. E to the negative, no, we are using 1. Oh, come on. So 1. And that's 3 plus 2 ln of 1, which is 3 plus 0, which is 3. And that's concave up. So second derivative gives us concavity. First derivative gives us increase and decrease. We should be able to graph from this point. We draw we don't have to concern ourselves with a negative, because we know that there is a barrier here and there's no function to the left. That's our y-axis, it's our x-axis. And now let's see what points do we have. So we have intercept at 1, 0. X-intercept at 1, 0. Let's put that here. Then we are supposed to get a minimum at 1 over root e. So we have to figure out roughly what the decimals are for this one. There are procedures later on in Calculus 1 that will let you, approximate the value. Right now we don't know those. So 1 over the square root of e is approximately 0.6. Comma, and now we have negative. And now you compute the second one. About 0.2, 0.18. So this is approximation for these values. So 0.6 negative 0.2, 0.6 negative 0.2 should be right there, and supposed to be a minimum. There we go.
A different answer for negative 1 divided by 2e.
Did you put parentheses?
Double check. Yep.
Got it? And we have a critical e to the negative 3/2. So e to the negative 1.5 is about 0.22, comma. negative 0.07. So it's almost 0.1. So now I see that all of these values that I have, are too small to graph, right? So I'm just going to spread out these numbers. So let's go with four units to B1, and then 0.6 would be here, so 0.2 would be somewhere over there. That's our minimum, so it's going to be a smiley face. Then we are going to have 0.22. Well, that's here. It's still too small, but it's hard to see. All right, so what do I have now? I have minimum has to go through x-axis and has to contain, this is, minimum is what? 1 over root t? This is 1 over root t. And this is e to the negative 3/2 values. So the function from 1 to root t better be increasing. Yep. And concave up. Awesome. Increasing and concave up. Concavity will change from concave up to concave down. Ooh, we do not have vertical asymptote. See that? No. The graph is not allowed to cross, guys. So we see the minimum, and we see concave up for the part that it's to the right of e to the negative 3/2. So that all fits. Now we need the concave down piece. So here, I need the concave down piece. And this is why this asymptote doesn't exist. Because the concave down piece is not allowed to cross x-axis. So it will continue, and it would have an open circle here, and it's very hard to see that little piece, but it's concave down. So it's decreasing, it's concave down to fit all of the specifications that are necessary, but there is an open circle from the origin going down. You know that your function square root of x starts at 0, 0. So that should not be weird. But we had definitely discovered that what we thought was the asymptote, that it's not an asymptote. I have no clue if I can erase these now. Yep, we have to get it off.
So that's why there's an open circle at the origin?
Yeah, we can't fit anything on the asymptote, so there is no asymptote. So I'm just going to go here and just cross it out. Because ln x should spawn an asymptote, and x squared is not going to spawn an asymptote. So obviously you have battle of two sides, right? Now which one does it win? Usually the one with the asymptote wins. But in this case, we see that the graph cannot follow that asymptote. And why the graph can't follow the asymptote? If you have the configuration, here is the asymptote, and here is the x-axis, and here is the point, the asymptote has to be followed like this, or like that. You have to follow the asymptote in one of the two ways. The top one is a no-go because it doesn't have, right?
It's
Exactly. So this one doesn't have an x-intercept there, so you can't do that. The other one has multiple issues. One is it spawns a maximum that it doesn't exist, and then so there's no way for asymptote to be there. So that's how you detect that there is no asymptote.
I don't get how you couldn't just do concave down and then bring the line down with the vertical asymptote.
Because I just explained that because it will spawn a maximum that was not detected by the first derivative test, right?
Okay.
If I have an asymptote like this and there is a point, this inflection point e to the negative 3/2 right there.
It's going to show that there's a maximum that we never.
Yes.
found.
So you can either go with the line up, which you can't because you will make an extra x-intercept you don't have, and to have a concave down, you would have to do this to have a concave down. But to have a concave down, that would make a maximum there that you don't have. So either for the top part of the line, there's no x-intercept. For the bottom type of the line that you would have to have in order for asymptote to be there, you don't have a max. So because those 2 points don't exist, then the vertical asymptote can exist. And the only solution to that issue is to have the open circle at 0, 0. And now, if you look at your, we can, again, something that you should be doing every single time is verifying when you are done with this, right, with the graphing utility. So we can use Desmos and just graph x squared times ln x. And there it is. It's a little bit hard to see that, but you can see all of the important points. And if you zoom enough, there is your minimum around 0.6, the open circle at 0, the x-intercept at 1, and then you see that this part here is concave down, and this part is concave up. So over here around 0.2 is the point that splits the two worlds.
Quite a stupid question, but when would it be a closed circle?
We can't have ln of 0, right? ln of 0 is each one of these values you need to be able to plug back in the original problem. Original problem is x squared times ln x. So ln x of 0 would create infinity.
It can't be 0 because yeah, it's in the domain 0 to
Open parenthesis, which means yes. So open interval. So we can't use x equals 0, so it must be open circle. And all of these obviously fit our graph. Now you can barely see the squiggle here, and then there is the U shape for the other side. Woohoo! The class ends in 1 hour and 40 minutes. Do you want another example? Or should we go with the review?
I'd go with the review.
Review? All right, we had 4 examples of this, so you can... all right, fine. Bye.